Hello everyone and welcome back. Hopefully your questions went well. So what we're going to do now is we're going to do basically the same process. However, now we're going to be looking at limiting reactants. So we're going to be given two concentrations and two volumes, and we're basically going to be asked to determine, well, which one's going to be limiting, and based off of that, we're going to be asked, well, what is the mass of our product that is going to be produced, which is in this case going to be aluminum hydroxide, which is going to be a solid. All right. So the process is generally the same. So this question is saying, well, Al2SO4 reacts with calcium hydroxide to form a precipitate of aluminum hydroxide. Determine the mass of aluminum hydroxide when 20 milliliters of 0.015 moles per liter aluminum sulfate is added to 30 milliliters of 0.0185 mole per liter calcium hydroxide. So first off, again, as we start every question, write the balanced chemical equation. So here we can see that we're reacting our aluminum sulfate with our calcium hydroxide in order to produce aluminum hydroxide. And because both of these have two, we're going to also have a byproduct of something else. However, writing our balanced chemical equation, we are going to have Al2SO4 3 plus CaOH2 reacting to produce aluminum hydroxide. Oops. And if aluminum hydroxide is produced, it will also create calcium sulfate. And that is going to be just CaSO4 because they're both going to have a charge of +2. So looking through this, we will have to do some balancing here. So our aluminum, I have 2 on this side, and I only have 1 on this side, so I'm just going to insert a coefficient of 2 there. With our SO4, I'm seeing that there are 3 here, there's only 1 on this side, so I'm going to need to have a 3 there, and then I'm going to also need to put a 3 here in order to produce. So I have 2 aluminum, 3 calcium, 6 hydroxide, and oh, that is supposed to be OH3. My bad. So there we go. That is a balanced equation. So the very first step that we need to do is calculate the number of moles of each reactant. So to do that, we can just use our number of moles. Our concentration equals our number of moles over our volume, right? And we are going to rearrange this equation to solve for moles. So instead, we can just multiply both sides by volume. So concentration times volume is going to equal our number of moles. So we are given concentrations and volumes of both Al2SO4 and CaOH2. So given both of these, what we can do is we can simply just do our concentration times our volume. So we're going to start with our Al2SO4 3, and our concentration of that is going to be 0.0150. So that is going to equal 0.0150 moles per liter times 20 milliliters. Well, that's in milliliters, but we have moles per liter here. So we are going to need to convert that into liters. So that is just going to equal 0.020 liters. All right. And that is going to give us, if I put it into my calculator very quickly, 0.0150 moles times 0.020 liters, going to give me 3 times 10 to the negative 4 moles. All right, and I'll just switch colors here for our calcium hydroxide. So our CaOH OH2, right, is going to have an initial concentration of 0.0185 moles per liter. We're going to multiply that by our 30 milliliters, which is going to be 0.030 liters. And that is going to end up giving us 0.0185 times 0.030, and that's going to give us 5.55 times 10 to the negative 4 moles. Now be careful here when determining your limiting reactant. You cannot just jump to the conclusion that because our aluminum sulfate has less number of moles, that this is automatically the limiting reagent, right, or the limiting reactant. Because sometimes with our molar ratios, that's not going to be true. And I believe in this solution, we are going to figure out just how that works. So down here on the bottom now, we're asked, well, let's determine the limiting reactant. So how do we do that? Well, we want to look and see which reactant is going to produce the least amount of product. So let's pick our product, might as well go for the one that we're going to be looking for in the end. So our aluminum hydroxide, or AlOH3. So if we look here, let's start with our aluminum. So our aluminum sulfate, right, has a coefficient of 1, right? So what we are looking for is always going to be on top. So we are going to put 2 moles of AlOH3 over top of 1 mole of Al2SO4 3. And if we set that equal to, our number of moles that we have, we're going to have X mole of AlOH3 over our number of moles of Al2SO4, which we calculated up here to be 3 times 10 to the negative 4 moles. Again, we're going to rearrange this equation, so it's going to be 3 times 10 to the negative 4 moles times 2 moles over 1 mole, giving us 3 times 10 to the negative 4. Oops. Oh no. 3 times 10 to the negative 4 times brackets 2 over 1, which is going to give us 6 times 10 to the negative 4 moles. All right, so that's telling us that if we were to react our aluminum sulfate with an excess of calcium hydroxide, we would get 6 times 10 to the negative 4 moles. So now we're going to do the exact same thing for our calcium hydroxide. So again, we're going to put what we're looking for, our AlOH3. Make sure we use the same one over here as we do here. So again, it is going to be 2 moles of AlOH3 over 3 moles, because we have the coefficient of 3 here, 3 moles of CaOH2. And that is going to be set equal to X moles over our number of moles of CaOH2, which is 5.55 times 10 to the negative 4, right? We'll rearrange to solve for X. So it's going to be 5.55 times 10 to the negative 4 times 2 over 3 is going to equal X moles, right? If I do that calculation here, it will be 5.55 0.55 times 10 to the negative 4 times 2 over 3. And that is going to end up giving us 3.7 times 10 to the negative 4 moles. So now, in order to determine which one is limiting, we have to look at how much aluminum hydroxide is produced from each scenario, right? If we were only using aluminum sulfate with excess calcium hydroxide, we would produce 6 times 10 to the negative 4 moles. If we were using only calcium hydroxide with an excess of aluminum sulfate, it would produce 3.7 times 10 to the negative 4 moles. So as we can see, this is going to be a smaller number. So therefore, our calcium hydroxide is going to be limiting. So therefore, we're going to use our value of calcium hydroxide for the remainder of the question, okay? Because we have excess of this. So this isn't going to determine what our final constant or our final amount of our aluminum hydroxide is. This will. So moving on, right? What we're going to do now is we're going to determine the amount of aluminum hydroxide that is going to be produced in moles. And luckily, by choosing to make our comparison with aluminum hydroxide, we have already figured that out here. It is going to be 3.7 times 10 to the negative 4 moles. All right, so that's the good part about using what we're looking for to determine our limiting reactant, is we save ourselves a step, right? We already have this mole value here, right? If I tried to determine my limiting reactant by calculating how much calcium sulfate was going to be produced, then I would have to do an additional molar ratio step in order to determine how much AlOH3 is produced, right? However, I already have calculated that, so now I just need to convert from moles to grams. So I'm going to show that my moles equals mass over molar mass, right? My number of moles is going to be 3.7 times 10 to the negative 4 moles. And my mass is what I'm looking for. My molar mass I can gather from the periodic table, and it will end up equaling, if I can find it here, 78.01 grams per mole. So with those two values, I can rearrange this equation to solve for my mass, right? So I just bring this over, multiply both sides by molar mass. So moles times our molar mass is going to equal my mass of my precipitate. So I'm going to take my moles, input them, times my molar mass, which is 78.01, right? My moles will cancel out, and that is going to equal 3.7 times 10 to the negative 4 times 78.01, and that is going to equal 2.89. So with significant figures here, right, it is just going to be 2.9 times 10 to the negative 2 grams. And that is going to be of aluminum hydroxide. So that is great. We have come to the final answer. So that is exactly how we would do that. So what I'm going to say now is I'm going to give you a bit of an option here. I'd like you to try sample problem 2 on page 419. This way you don't have to listen to me talk anymore, because I know my voice must be getting annoying. However, I want you to try that one on your own, right? There is a worked example, so it'll show you exactly how to take each step. Some of their examples are a little bit different than the ways I do things. However, the general steps are overall the same, just they show their calculations a little bit differently, all right? If you are very stuck, right, I am going to be calculating a worked answer of this right following this here. So if you'd like to pull up your laptops, scroll to minute 16 of the recording, and you'll be able to see me do that worked example. But I'll allow you, if you don't feel like it, to just get to work, right? And once you're completed that, please complete questions 21 to 30 on page 420 of your textbook, right? So enjoy your weekend, everybody. And like I said, if you would like to stick around and watch the worked example of our final question, feel free to do so. If you're feeling fairly confident, want to do it on your own, feel free to turn me off and go ahead and work on your own. All right, have a good weekend. All right, so for those of you who wanted to stick around, we're going to look at one more question here. This is the sample problem 2 that everybody else will be working on in class. However, I will actually work through exactly how to do it. So what we're going to look at now is a chemist is going to want to react 60 milliliters of 0.135 mole per liter sodium oxalate, right, which is Na2C2O4, with 0.226 mole per liter calcium chloride to precipitate calcium oxalate, right? So this is the two-part question. First thing it's asking us is what is the minimum volume of calcium chloride that is needed in order to make this reaction complete fully, right? And then finally, what is the mass of CaC2O4 that will be produced, right? So again, starting with our balanced chemical equation, right, we are going to have our sodium oxalate, so our Na2C2O4, that is going to react with calcium chloride in order to produce calcium oxalate, and NaCl. Now if we look here, we have 2 NAs, so I just have to put a coefficient of 2 here, right? And that is a fully balanced equation, right? So just be careful. This is a solid. The rest of these are aqueous solutions. All right, so the first step, again, just like everything else, finding the moles of our Na2C2O4. So if we look up in our question, right, we have a volume and we have a concentration. So again, we can use our equation, that is concentration equals our number of moles over our volume, all right? So we're going to rearrange this again, just like the previous question. So concentration times volume equals the number of moles. So if I take my concentration of 0.135 moles per liter, and I'm going to multiply that by my volume of 60 milliliters, which would actually end up equaling 0.060 liters. And that is going to end up giving me a number of moles of 0.135 times 0.060, 8.10 times 10 to the negative 3. So we'll just write 8.1 times 10 to the negative 3 moles. So there we've done the first step. We've calculated our number of moles. So now we need to use our mole ratio in order to determine the number of moles of calcium chloride that are required so that we can react every single mole of our Na2C2O4. So again, we just pull out our mole ratios. Our CaCl2, we can see, has a coefficient of 1, and our Na2C2O4 also has a coefficient of 1. So this makes it really, really easy for us. It's just going to be a 1 mole over 1 mole ratio, which is going to be equal to X moles over our concentration, or our number of moles of Na2C2O4. Again, we have our Ca2 on top, right? So that is just going to be divided by 8.1 times 10 to the negative 3. And if we rearrange this, it's going to equal 8.1 times 10 to the negative 3 times 1 over 1. Obviously, if we're multiplying anything by 1 over 1, our number of moles of CaCl2 required is just going to be 8.1 times 10 to the negative 3 moles of CaCl2. All right, so we have that. That's perfect. So using that value there, what we can do is we can move on to the next step, which is using our number of moles and our concentration of CaCl2. So our number of moles and our concentration. So if we go back to our question, well, we found that our concentration is 0.266 moles per liter. So I can sub that in here, 0.266 moles per liter. All right, and my number of moles we figured out at the very end there is 8.1 times 10 to the negative 3 moles. So that equals 8.1 times 10 to the negative 3. And again, we are going to use our concentration equation, except for this time, we are finding volume. So what I'm going to do is I'm going to write out my concentration equation. C equals our number of moles over our volume. We have concentration and moles. So what we will have to do is we will have to swap our C and our V, which is actually a two-step process. So we would multiply everything by V, right, which would give us C times V equals N. And then we would, little n, and then we would divide both sides by C in order to give us volume equals our number of moles divided by our concentration. All right, so using this here, I can just sub in my values. So for my number of moles, so my volume is going to equal 8.1 times 10 to the negative 3 moles over 0.266 moles per liter. All right, and once I do that calculation, 8.1 times 10 to the negative 3 divided by 0.266 moles per liter, it is going to give me 3.0 times 10 to the negative 2 liters. All right, remember, our moles are going to cancel out here. We are going to be left with liters. So if we wanted to convert that to milliliters, that is going to just be 30 milliliters. Okay, so that is the first step. That's our first question that they were asking us for. Well, how much solution do we need? Well, we found the volume here, right? You can express it in either milliliters or liters. I don't mind either way. And then finally, you're going to use your mole ratio to determine the number of moles of CaC2O4. So if we go back here, luckily we have a 1-to-1 ratio again, right? So that makes things very, very simple for us, right? So our number of moles of CaCl2, so we're going to put that on the bottom, is going to be 1 mole CaCl2. What we're looking for is going to be on the top. It'll be 1 mole CaC2O4 is going to be set equal to X moles of CaC2O4 divided by our number of moles of CaCl2, which we calculated up here to be 8.1 times 10 to the negative 3 moles. All right, we'll rearrange again. So I'm going to multiply both sides by 8.1 times 10 to the negative 3. Of C2. multiplied by 1 mole CaC2O4 over 1 mole of CaC2. Our moles of CaC2 are going to cancel. We are just going to be left with moles of CaC2O4. So if I just look at that, 8.1 times 1 over 1 is just going to give us 8.1 times 10 to the negative 3 moles of our CaC2O4. All right, so there we go. We have calculated our number of moles that are going to be produced. And then finally, our last step there is just going to be calculating the number of moles of our calcium oxalate, or our CaC2O4. So I'm just going to take our number of moles. So our remember, moles equals mass over molar mass, right? Our number of moles is going to equal 8.1 times 10 to the negative 3. And our molar mass is equal to, if you look on the periodic table, 128.1 grams per mole. So I can sub those things in, right? Obviously, I'm going to have to bring my molar mass over. So molar mass times moles equals mass. So 8.1 times 10 to the negative 3 times 128.1 grams per mole, this is moles, is going to give me 8.1 times 10 to the negative 3 times 128.1 moles, grams per mole, right? And that's going to give me 1.04 grams. With significant figures, we can actually round that to 1.0 grams. All right. Oh, sorry. Didn't include that last little bit there. So with that being said, that pretty much wraps up all of the sample problems. So hopefully that you guys are doing all right with this. If you have any questions, feel free to let me know. If not, again, try and go back over the weekend if you have some time. Complete your practice problems on 420 to make sure that we're ready to go for Monday once we get back to school. All right, have a good weekend, everyone.